Question number 81 says which cationic species is more stable in which of the following pairs? So over here one has to remember that carbo cation stability is directly proportional to number of hyperconjugative structures directly proportional to resonance structures. Okay, from hyperconjugation we get the idea that 3 degree is more stable than 2 degree, which is more stable than 1 degree carbocation. Now if we draw the resonance structures of the pair X, what we will find is as follows. In both the structures it is 1 degree, right? What about the other structure? So first one is 1 degree, second one is 2 degree. So obviously structure 2 is more stable. That means this one is more stable. For the next one in pair Y, one should remember that the negative charge is more stable on most electronegative atom and vice versa. That means positive charge should be stable on least electronegative atom. So if we consider that way, let us write the resonance structures. That is one way of writing. So here we can see the positive charge is on either of the nitrogen atoms, but over here among the two resonating structures, it can be either on oxygen or it can be either on nitrogen, but it should be most stable on nitrogen. So these two are equivalent structures leading to more stability, whereas this and this is non-equivalent structures leading to less stability. So here we will see number 3 is more stable. So that way if we think, we will say 2, 3 is the correct option over here. Question is which of the following structures is non-aromatic? So for non-aromatic, either of the things, if it is satisfying, then it will be non-aromatic. That is, it is having, or it is non-cyclic, it is non-planar, okay, then we can say it is non-conjugated, so in either of the cases we will say it is going to be non-aromatic. So the first one we can see It is basically a 10 pi electron system, cyclic, conjugated, follows the 4n plus 4n plus 2 pi electron Huckel rule, and should be aromatic. Okay. For the next one also, it is a 6 pi electron system and cyclic, conjugated, 4n plus 2 pi electron system. Huckel rule it follows, so it is also going to be aromatic. For the next one, though it is a 10 pi electron system, there are some transannular hydrogens which will undergo repulsion among them, and so even though it is cyclic, it becomes non-planar, and so it will be non-aromatic compound. This one over here, obviously it is phenanthrene, and it is a, over here we can say it is 14 pi electron system. It is cyclic, it is conjugated, follows the 4n plus 2 pi electron system, and it is aromatic. So option C over here is the correct option. Next question, ortho oblique para effect of the methyl group in electrophilic substitution reaction of toluene is due to. So over here let us think a toluene system, and there is the CH3 group, and in the rate determining step, suppose the electrophile comes, the pi bond opens up, creating a sigma complex such as the following shown over here, and now one can see that this aranium ion which is formed over here, the positive charge over here is being stabilized by the plus I effect of the CH3 group. Okay, so over here our answer is going to be, since the rate determining step is being controlled by the inductive effect which operates through a sigma bond, okay, and then subsequently the hydrogen is lost, and over here one can say this will be the product formed. So either the product can enter the ortho group, or it can also come in the para position via this intermediate. So if it is joined over here, then one will say obviously this type of intermediate will be formed. Now if we do the resonance, then one can see that again the positive charge can be stabilized by the methyl group. So we can say that the orthopara directing of the methyl group in electrophilic substitution reaction of toluene is due to, both in the cases of ortho or para product, due to inductive effect. Okay, so subsequently one can think that the hydrogen is lost like that, and So in that case, well, let's do another resonating structure and then we will lose the hydrogen. So it is over here. And subsequently we have the product formed. So the correct option is option A. Question number 84. Over here we have to find out the relative order of basicity of the following amines. First of all, the first thing that we should remember always that aliphatic amines are more basic than aromatic amines. First thing. Okay. Then we can say electron donating groups and orthosubstituted anilines are more basic than only anilines because of SIR, that is steric inhibition of resonance, the SIR effect, and electron withdrawing groups decrease basic city or basic character by making the lone pairs less available for donation. Okay. So that way if we consider, then we will say triethylamine rather, that is C2H5 whole thrice, which is aliphatic amine, will be more basic than the one which is having steric inhibition of resonance operating over here, coming from the CH3 groups at the ortho position, and that should be followed by the simple aniline and that should be followed by alanine, which is connected to the nitro group at the para position, because this is a electron withdrawing group, the NO2, and over here we have SIR effect. Okay, so for that, if we consider, the correct answer for our question will be B. Next we have which molecule in each of the following pair has the highest dipole moment. Now in this case, for one, question is which molecule in each of the following which molecule in each of the following pairs has a higher dipole moment. So among 1 and 2 we have to tell which is having higher dipole moment. Now that way, if you think that this can exist like this, okay, then we are getting negative charge permanently on the oxygen, positive charge over here, and this is basically, we will say, a 2 pi e electron system. Your cyclic, that is conjugated, and aromatic, and also is following the 4n plus 2 pi electron system, right? So that way this will be more polar. Okay, this is more polar because of the permanent separation of charge, whereas over here this is delta plus and this is delta minus because of the higher electronegativity of the oxygen. So one is more polar than that of the two, that is means higher dipole moment. For the pair number y, and among 3 and 4, if we think that this way the structure can show some resonance, so we are having a negative charge over here, okay, and then we have the cyclic hepta trinyl cation, okay, something like that. So because of this type of charge separation, this unit over here is aromatic and that also is aromatic, okay. So if we consider that way, this is 6 pi electron system, this is also 6 pi electron system, and the dipole moment will be lying in this direction. But however, if we try to create either way charge separation, if we do a charge separation like that for the compound number 3, what we are going to find is that it leads to the formation of one aromatic system, but the other one is anti-aromatic. This is a 4 pi E electron system, which is anti-aromatic. So there is no separation of charge in this molecule 3. So that means molecule 4 will be having higher dipole moment than that of the 3. So over here our answer will be obviously 1 and 4. That is option number 4.